All right, in this video, I'll be going over section 8.2. Section 8.2 is about Maclaurin series and Taylor series. Okay, so basically, we will be formally defining the Maclaurin series and the Taylor series, and we will be going over some examples on how to calculate the Maclaurin and Taylor series for certain functions. Okay. In this section, we are going to stick to these notations. If 0x means f of x, it is just the function f of x. F1, you put a 1 inside parentheses top here. F1 of x means the first derivative of f of x, df of x over dx. That is the first derivative of f of x. And then f2 x means the second derivative of f of x. Okay. Similarly, f3 of x means the third derivative of f of x. Okay. So we are going to stick to this notation from here onwards. Okay. All right. I want to start by defining the Taylor polynomial and the Maclaurin polynomial for a given function at a given point x naught. Okay. So let's go over this definition. Definition 8.6. Let f be a function with an nth order derivative at the point x naught. X naught is a fixed point. Okay, we define the nth Taylor polynomial for f at x naught to be the function which is denoted by Pnx is equal to sigma k goes from 0 to n fk x naught divided by k factorial times x minus x naught to the power k. Here again, notice that this fk x naught means the kth derivative of f of x at x naught, because you have plug in x naught here. That means you take the kth derivative and plug in x naught in the kth derivative. Okay, so that's what it means. And of course, you know what is the factorial. Factorial k means 1 times, 2 times, you take the product up to k. Okay, and if you of course expand this summation by plugging k is equal to 0, 1, 2, 3. Notice that the starting index is 0. So if you plug in k is equal to 0, 1, 2, 3, 4, these are the terms that you will be getting. This is the first term, and this is the second term, this is the third term, and so on and so forth. Okay, up to nth term. Okay, so because you have to continue your sum up to n, that's it. And then this series is given a special name when your x naught is equal to 0. Remember, I told you that x naught is a fixed number. If that fixed number is 0, we give a special name for the Taylor polynomial for f at x naught. That special name is Maclaurin polynomial for f. Okay, remember, when x naught is equal to 0, you get the Maclaurin polynomial for f. So Maclaurin polynomial is given by Pn of x is equal to sigma k goes from 0 to n fk of 0 divided by k factorial times x to the power k. All what you do is you put x is equal to 0 here, pardon me, x naught is equal to 0 here, and x naught equal to 0 here. Then you get this one. This is what we call the Maclaurin polynomial for f. All right, those are the definitions of nth Taylor polynomial and the nth Maclaurin polynomial. Okay, this is the nth Maclaurin polynomial, and this is the nth Taylor polynomial. You say n because you take the summation up to n. All right, let's move on. Let's go over this example now. Here is the example that I want to look at. Graph the exponential function ex along with its first, second, and third Maclaurin polynomials. Okay. First of all, let me recall the Maclaurin polynomial again. Let's take here f of x to be e to the power x. That's the given function, right? E to the power x is the given function. So that's going to be my f of x. For this f of x, I want to find the first, second, and third Maclaurin polynomials. Okay, so you will see the importance of those Maclaurin polynomials in a second. I'll show that to you. Before that, let me write the definition of the Maclaurin polynomial. For the Maclaurin polynomial, I will use MP, Maclaurin polynomial. I will note it here. I'll use MP, okay? Maclaurin polynomial. Okay, that's going to be, what is that going to be? Sigma k goes from 0 to n, 0 all the way up to n, fk of 0 divided by k factorial times x to the power k. That is the nth Maclaurin polynomial. Okay, so now we are asked to find the first, second, and third. Let's find the first Maclaurin polynomial. Let me denote this by Pn. Okay, Maclaurin polynomial. This is Pn. It should be Pn of x, just like in the definition. So we are asked to find P1 first. Let's find P1. What is P1? When n is equal to 1, you take the summation from k is equal to 0 to 1, because your value of n is 1. This is 1 means the summation should go up to 1. So this is going to be, what is this? This is going to be f k of 0 divided by k factorial times x to the power k. Now you need to expand this, of course. So how do you expand this? Well, before we expand this, let's observe something here. We are working with f of x is equal to e to the power x, right? Then notice that any order derivative, fk of x, is again e to the power x itself, right? Because no matter how many times you take the derivative of this one, the derivative of e to the power x is e to the power x itself. Okay, so any order derivative of this function would be again e to the power x itself. So we need in this formula fk0 here, right? In this formula, this is the coefficient of the k term. That is going to be, actually this is going to be the k plus 1 term. So we can find fk0 by plugging 0 here. If I plug in 0, that's going to be e to the power 0, which is 1. That means this quantity is always 1. So I can plug in 1 here. So this is going to be sigma k goes from 0 to 1 over k factorial times x to the power k. Okay, now I can take this summation. This is going to be, if you plug in k is equal to 0, what would you get if you plug in k is equal to 0? If you plug in k is equal to 0 here, that is x to the power 0, which is 1. What is this? 1 over 0 factorial. Notice that 0 factorial is defined to be 1. We take 0 factorial to be 1 always, okay? So this, the first term is going to be 1. And then if you plug in k is equal to 1, you plug in k is equal to 0 first, and then you plug in k is equal to 1, because you need to continue up to 1. Okay, if you plug in 1, you get just x, right? Because you know that 1 factorial is just 1. And remember, 0 factorial and 1 factorial, both are 1, okay? Both are 1. So this is just 1 plus x. And then we need to find P2x, the second Maclaurin polynomial, okay? So how do you find P2? That is going to be k goes from 0 to 2 this time. Not 1, it is 2, because you are looking for the second polynomial. Again, you need to have this piece here, but we know that if k of 0 is 1, it is 1 for any k. So let me plug in 1 there. 1 divided by k factorial times x to the power k. This is going to be 1 plus x. Of course, these two terms should be there, because if you plug in x is equal, k is equal to 0, you get the first term here as you got here. So it's going to be 1. And then if you plug in k is equal to 1, you get just x. And if you plug in k is equal to 2, you get x squared divided by 2. Okay, this is the second Maclaurin polynomial. Okay, so and then we want to find the third Maclaurin polynomial. So I'm not going to show the calculation here. I will just write the answer. This time k goes from 0 to 3, 1 over k factorial times x to the power k. If you expand this, you should get 1 plus x squared over 2 plus x cubed over 6. Okay, these are the three Maclaurin polynomials that we were asked to find. Okay, now I'm going to graph these three Maclaurin polynomials along with the original function f of x. Okay, you will see that something interesting happening here. If you look at these graphs, notice that in black color is the actual graph of e to the power x. Okay, and as you can see, this is the graph of p1x, and in purple is the graph of p2x, and in green is the graph of p3x. As you can see, the graph of p3x is very close to the graph of actual function f of x is equal to e to the power x, right? As you can see, this black graph and the green graph, they are very close to each other. What that tells you is that when you take this n to be larger and larger, it approximates your original function better and better. Okay, this function approximates your function, actual function e to the x, better than this does, right? Clearly, because this graph is more closer to the actual function. That's the idea. For example, if you compute the 50th Maclaurin polynomial, you will see that that 50th Maclaurin polynomial almost overlaps with this original function f of x is equal to e to the x. Okay, that's the idea. That's the importance of this Maclaurin polynomials, and of course Taylor polynomials as well, which we will be discussing in 2 minutes. All right, let's move on. Now I want to define the Taylor series. Okay, so here is the definition. This is definition 8.7 in the textbook. Let f be a function with derivatives of all orders at the point x naught. We define the Taylor series for f at x naught to be the following power series in x minus x naught. Okay, this is what we defined as the Taylor series. This time k goes from 0 to infinity, not up to n this time. Remember in the previous case, when we defined the n Taylor polynomial, we stopped at n, right? But this time we continue up to infinity. K goes from sigma k goes from 0 to infinity. Fk x naught divided by k factorial times x minus x naught to the power k. This is what we call the Taylor series for f at x naught. Okay, and then like in the previous definition, we have a Maclaurin series in this case. Maclaurin series means your x naught is equal to 0. If you plug in x naught, if your x naught is equal to 0, then we say that the corresponding series is the Maclaurin series. What would you get if you plug in x naught is equal to 0? This is what you get. You put x naught is equal to 0, so you get 0 here. This is just x to the power k. This is what we call the Maclaurin series. Again, notice that this is from k goes from 0 to infinity, not up to n. Okay, and if of course if you write the expanded form of this, this is what you get. If you plug in k is equal to 0, you just get f of 0, and if you plug in k is equal to 1, you get this term, so on and so forth. Okay, you can easily take by plugging k values in this k term. Okay, all right, let's move on. Next, I want to work on this example. Find the Maclaurin series for the exponential function e to the power x, and find the interval of convergence for the series. Okay, first of all, recall that we are dealing with f of x is equal to e to the power x. That means any derivative fk of x is again e to the power x itself. That means fk of 0 is equal to 1, because if you plug in x is equal to 0 here, e to the power 0, which is 1. Okay, so we know that. That means if you are dealing with the Maclaurin series of this one, first of all, notice that the Maclaurin series of this one would be here, would be this one. Okay, this expression, that is k goes from 0 to infinity, fk of 0 divided by k factorial times x to the power k. According to the definition, this is the Maclaurin series. Now, the good thing is that I know fk0. fk0 is 1. I can plug in 1 there. So the Maclaurin series is just k goes from 0 to infinity 1 over k factorial times x to the power k. That is the Maclaurin series. It's so easy to find because any derivative, any order derivative is e to the power x itself. Okay, but for other functions it could be complicated because you need to find the derivatives of various orders, right? Then you have to keep differentiating, and when you get different things, it could be more complicated. But for luckily for e to the x, it's going to be very simple, and this is the Maclaurin series for e to the power x. Okay. All right. Now we are asked to find the interval of convergence for the Maclaurin series for e to the power x. Okay. For that, what are we going to do? We are going to use theorem 7.42. That means we are going to calculate rho. To calculate the interval of convergence for this series, we are going to calculate the rho. Rho is defined to be, remember, rho is defined to be the limit as k approaches to infinity. As k approaches to infinity, bk plus 1 over bk. Don't forget the absolute value around them, around that expression. Okay, we are following a similar procedure as we did in section 8.2 to find the interval of convergence and the radius of convergence, of course. Okay, this is going to be limit k approaches to infinity. What is bk plus 1? By the way, what is bk? bk is this expression, the general term of your series, bk. Okay, bk plus 1 is going to be x to the power k plus 1 divided by k plus 1 factorial, divided by bk is just x to the power k divided by k factorial. And if you simplify this, it's easy to simplify this using the reciprocal rule. You will get exactly absolute value of x times. Let me actually do the reciprocal rule here. K plus 1 divided by k plus 1 factorial times k factorial divided by x to the power k. These two can be easily simplified. Here you have x to the power k plus 1, x to the power k in the bottom. That means it's just x in the top, right? I'm forgetting something important here. Put the absolute value. Okay. All right. This is going to be equal to limit k approaches to infinity. I have absolute value of x in the top, and then how do we simplify these two? K factorial and k plus 1 factorial. Remember, k factorial is 1 times, 2 times, 3 times, all the way up to k. K plus 1 factorial is 1 times, 2 times, 3 times, all the way up to k plus 1. Then if you simplify those two, you just get 1 over k plus 1, right? 1 over k plus 1. That's what you get. Now, notice that I don't put the absolute value here because this is a positive expression. Okay. Now, if you take the limit as k approaches to infinity, this is clearly 0 for all x, no matter what the value of x. This is going to be 0 as k approaches to 0. As a result, this product is 0. Okay. So what does that tell you? That means the rho value is 0. 0 means 0 rho value means rho is equal to 0 means it's less than 1 by theorem 7.42. Theorem 7.42, the series, the Maclaurin series. K goes from 0 to infinity, 1 over k factorial times x to the power k converges absolutely. Absolutely for all x. That means interval of convergence is going to be minus infinity comma infinity, or equivalently you could write R, set of all real numbers, and the radius of convergence RC, radius of convergence, is going to be infinity. But it's the length of the half of the length of this interval, which is clearly infinity. Okay. All right. That completes that example. Let's move on. Next, again, I want to walk you through an example. Here is the example I want to look at. Find the Taylor series for ln x at x is equal to 2 and the interval of convergence for the series. Okay, how do you find the Taylor series for that? Well, first of all, let's recall the definition. Taylor series of a function at x is equal to 2 is given by this expression by definition, right? That is sigma k goes from 0 to infinity. Fk, because you need the Taylor series at x is equal to 2, you plug in 2 here. Fk2 divided by k factorial times x minus 2k. This is x naught. Your x naught is 2 in this case. That's why I'm plugging x naught here, x naught here. Okay. I'm just applying the definition. Let me write this. You could view this as x naught. Okay, this is my goal. I want to find this series. Okay, for that, what I'm going to do is always, if you're asked to find the Taylor series for a given function, always you need to identify this term, this general term, fk2 divided by k factorial. If you can identify this term, then we have a pattern. You can write the summation as a formula. Okay, so the goal is to find a general expression for fk2 over k factorial. Okay, let's do that. We can achieve this via a table. Okay, here is how you construct the table. First of all, you start with k is equal to 0 because this series starts at k is equal to 0. You put k is equal to 0 first, and then 1, 2, 3, 4, so on and so forth. And this is the kth value. My goal is to get a general expression when your index is k. Okay. So if I have a general expression, I can write the formula here. Okay, I can put that general expression here and write the formula. Okay, so here is what I'm going to do. When k is equal to 0, this is the first column, and then the second column is fkx. Remember, fkx means the kth derivative of f of x. And then I plug in x naught is equal to 2 in this derivative. You find the derivative of fkx, and then you plug in x naught is equal to 2 in that function. X is equal to 2 in that function because I'm interested in, I need 2 here, right? fk2. That's why I'm plugging 2. And then finally, I divide that fk2 by the k factorial because I need this quantity. fk2 divided by k factorial. That is exactly this. So it's all about completing these 4 columns. Once you complete these 4 columns, then you have a general formula for fk2 divided by k. Okay. All right. Let's see how to complete this table. So now you need to find what you put here, what you are going to put here, right? This is when k is equal to 0. If you put k is equal to 0 here, that is just f of x, right? Remember in the notation that I introduced, f0x means just f of x. F of x is ln x. I take my f of x to be ln x. That's the function that we are dealing with. Okay. All right. Now if you plug in 2, x is equal to 2 in this function, you get ln2, okay? Because you need fk2 here. So you plug in x is equal to 2 in this function to get this expression. That is ln2. And then finally, you divide it by k factorial. K is 0 in this case. You divide it by 0 factorial. Remember, 0 factorial is 1. This is not 0, this is 1, okay? No typo here. 0 factorial is 1. So if k2 over k factorial is ln2 when k is equal to 0. Similarly, you calculate this row when k is equal to 1. Okay, when k is equal to 1 here, this is f1x. F1x means the derivative of f of x. The derivative of f of x is the first derivative. Okay, when k is equal to 1, you take the first derivative of f of x. The first derivative of f of x is 1 over x because your f of x is ln x. You take the derivative of this one and put it here, that is 1 over x, and then you plug in x is equal to 2 to get f1 of 2. That is, if you plug in x is equal to 2 here, you get 1 over 2. In the second column, always you plug in x is equal to 2. That's it. And then finally, you divide everything by 1 factorial. When k is equal to 1, The 1 factorial is just 1. So that is going to be just 1/2. And then when k is equal to 2, this is f2x. F2x means you need to take the derivative of this function. Okay, this is f1x. You need to take the derivative of this one more time to get the second derivative. If you take the derivative of this one, it is going to be this function. Now you plug in x is equal to 2 in this function to get f2 of 2. So this is that one. And then you need to divide this by the factorial of 2 because the k value is 2 in this case. If you divide that, you get this one. Now you need to continue this pattern, okay? And then you do the calculation for k is equal to 3. The third derivative, that means you differentiate this one, then you get this function. And then you plug in x is equal to 2. If you plug in x is equal to 2, if you plug in x is equal to 2, this is what you are going to get. And then you divide it by 3 factorial. If you divide it by 3 factorial, you will get this. Now, by following this pattern, by looking at this pattern, you should be able to write the kth term. Okay, when index is k, what is the kth derivative? Okay, by looking at this pattern, you should be able to see that the sign is alternating. This is plus, this is minus, this is plus, this is minus. So we need to have something like -1 to the power k minus 1 for k. But here in this case, you will see that k minus 1 is the right indexing that you need to have, right power that you need to have for -1. And then, of course, this pattern, you should be able to identify this pattern. This is going to be 1 over when you take the k derivative. This is 1 over k times 2 to the power k. Okay, that is by observing this pattern. For example, if you simplify this one, this is going to be minus 1 over 4 times 2 to the power 4. Okay, so when that is k is equal to 4, so that is 1 over 4 times 2 to the power 4. So when k is equal to k, or in other words, the kth derivative, when you take the kth derivative, this quantity will be equal to -1 to the power k minus 1 times 1 over k times 2 to the power k. Okay, so this is the general term. But notice that this general term is valid for all these terms. All these terms can be generated by plugging k is equal to 1, 2, 3, 4, 5, 6, but you cannot generate the first term because it does not fall within this pattern. The first term does not fall within this pattern. So what you do is you write the terms that fall in this pattern, within this pattern. Okay, so I'm going to write this series. This is the Taylor series that I'm looking for. This is going to be equal to, I'm going to separate out the first term. I plug in k is equal to 0. If you plug in k is equal to 0, of course, you get if you plug in k is equal to 0, you can easily find this quantity, that is exactly this one, because that is fk2 over k factorial when k is equal to 0, that is ln2 times when k is equal to 0, of course, this quantity is 1. So this becomes ln2, the first term, and then I'm writing the remaining term as a summation. Now, starting index is 1, because I took off the first term when k is equal to 0. So now I let the index run from 1 to infinity. This is going to be fk of 2 divided by 2 factorial times x minus 2 to the power k. Now the good thing is when k is equal to 1, 2, 3, 4, 5, I have a pattern. For all these, I have a pattern, the general term. I have a general term. The general term is this term. Because I can generate all these terms by plugging k is equal to 1. If you plug in k is equal to 1 here, you get this one. And if you plug in k is equal to 2 here, you get this one, so on and so forth. Okay. All right. Now I can plug in the general formula, general term for fk2 divided by this is k factorial, of course, not 2 factorial. k factorial. Okay, sigma k goes from 1 to infinity. My general term is minus 1 to the power k minus 1 times 1 over k times 2 to the power k times x minus 2 to the power k. Okay, I'm plugging my general term for this one. If k2 divided by k factorial is this one. Okay, this is the general term. So I plug that in here. Okay, now we found the Taylor series. This is the Taylor series for that. This is going to be our Taylor series. Now we need to determine the interval of convergence for the series. Okay, how do you find the interval of convergence? Notice that this is the Taylor series, and this first term is a finite term. So I don't have to worry about this term. All I need to check is this series. If this converges, that's where the entire series converges. Okay. All right. So let me analyze this series. So to find the radius of convergence, interval of convergence for this series, I'm going to use again theorem 7.42. Okay. Let me calculate rho. Rho is equal to limit as k goes to infinity, bk plus 1 over bk, the absolute value around them, is equal to, I'm going to have a giant expression here. Notice that your bk in this case is this term. Okay, so bk plus 1 would be minus 1 to the power k minus 1 divided by, this should be k, right? Because I'm replacing k by k plus 1, then you get k. In the bottom, you get k plus 1 times 2 to the power k plus 1 times x minus 2 to the power k plus 1 divided by minus 1 to the power k minus 1. It is just bk, right? K times 2 to the power k times x minus 2 to the power k. Don't forget the absolute value around it, okay? And I'm forgetting one more thing here. Take the limit. Take the limit of this, okay? Limit k approaches to infinity. All right, now I'm going to do some simplification here, okay? I'm not going to show all the work here because you're familiar with this kind of things. If you take, if you simplify this absolute value, this is what you're going to get. X minus 2, the absolute value of x minus 2 times k divided by 2 times k minus 1, k plus 1, pardon me. That's what you get. Now you need to find the limit. You need to find the limit. What is the limit of this one? Can you tell me what is the limit of this one as k approaches to infinity? Notice that this has nothing to do with k. The k is only here. So the limit as k approaches to infinity, this one is 1/2. This is going to be absolute value of x minus 2 divided by 2. Now for absolute convergence, we need, for absolute convergence, what do we need? We need this quantity to be less than 1, right? Your rho has to be less than 1. This should be less than 1. That implies that x minus 2 should be greater than minus 2 and less than plus 2. What I do is I multiply this 2 to the other side and then I remove the absolute value. Then x minus 2 should be between minus 2 and plus 2. That tells you that, that implies that x is between 0 and 4. Okay, so the interval of convergence includes the interval 0, 4. Now we need to figure out what happens at the endpoints, these endpoints 0 and 4. Let's analyze that. When x is equal to 0, I'm going to let me write when x is equal to 0, I'm going to go to my original series and plug in x is equal to 0 here. If I plug in x is equal to 0 here, what would I get? Let me plug that in there. Then I'm going to get sigma k goes from 1 to infinity minus 1 to the power k minus 1 divided by k times 2 to the power k times, remember that should be x minus 2 to the power k, but I am plugging x is equal to 0. Okay, so that is 2 minus 2 to the power k. It should be minus 2 to the power k. Okay, now if you simplify this, you should be able to see that this is going to be minus times k goes from 0 to infinity 1 over k. Do you see that? That's because you can write this as minus 1 to the power k times 2 to the power k. That 2 to the power k will be cancelled with this 2 to the power k. So you have a minus 1 to the power k here. And if you multiply these two together, minus 1 to the power k minus 1 times minus 1 to the power k, that is just minus 1. I pull that out. Okay. All right. But we know that this diverges. This is the harmonic series, right? This is the harmonic series. Harmonic series. It diverges. Okay. So that means series diverge at x is equal to 0. Series means the series that we were analyzing, this series. Series diverges at x is equal to 0. And also, I'm going to let you show that if you do the other analysis, when x is equal to 4, analysis at the other endpoint, you should be able to show that series converges conditionally. Series converges conditionally. That means this implies that interval of convergence is going to be 0, 4, 0 excluded because at 0 it diverges, but 4 included because at 4 the series converges conditionally. Okay, so the radius of convergence in this case, RC, radius of convergence is 2, half of the length of this interval, which is 2. Okay, by the way, what do you mean by converges conditionally? You might want to recall the definition. Okay, conditional convergence from chapter 7. It is your original series converges, but the absolute value series diverges. If that is the case, we say that the series conditionally converges. All right, let's move on. Okay, next I want to go over this example. Graph the Taylor polynomial of degree 1, 2, and 3 for ln x at x is equal to 2. Okay. Notice that by definition, the Taylor polynomial Pnx is going to be k goes from 0 to n, only up to n, because we are talking about Taylor polynomial. Okay, it's not Taylor series. Okay, so that's going to be fk of 2 divided by k factorial times x minus 2 to the power k. Notice that your x naught in this case 2, that's why I'm plugging 2 here. Okay, you have 2 here instead of x naught in the definition. All right, so now what are we supposed to do? We are asked to find the first, second, and third Taylor polynomials. Okay, so how do you find these polynomials? All what you need to do is you need to plug in n is equal to 1, 2, and 3. If you plug in n is equal to 1, you get P1 of x, that is the first Taylor polynomial, degree 1 Taylor polynomial, that is going to be, by definition, k goes from 0 to 1 if k of 2 divided by k factorial times x minus 2 to the power k. If you expand this, what would you get? This is going to be equal to, if you plug in k is equal to 0, you get f0 of 2. Remember, f0 of 2 is, of course, we need to have parentheses here. What is f0 of 2? It is just f of 2. When k is equal to 0, that is the original function, okay? f0 of 2 is just f of 2. F of 2 divided by 0 factorial. 0 factorial is defined to be 1. Okay, 0 factorial is 1. This is just f of 2 plus, what else? Next, you plug in k is equal to 1. If you plug in k is equal to 1 here, you get f prime of 2 divided by 1 factorial times x minus 2 to the power 1. You have to have power 1 here. I don't really have to write 1 because it's just that expression itself. Okay, so this is the first Taylor polynomial or the degree 1 Taylor polynomial. All what you need to do is you need to find this one. Okay, f of 2. How do you find f of 2? Your f of x was ln x, right? The given function is ln x. Let me actually write it. Your f of x is nothing but ln x. So you can find f of 2 by plugging 2 here. That is ln 2 plus. Next, you need to find f prime of 2. F prime of 2 you can copy from the table. F prime of 2 is just this one, right? F prime means f1, the first derivative. K is equal to 1 means the first derivative. First derivative, f1 of 2 means 1/2. It's just 1/2. 1/2 times x minus 1, x minus 2 here. Pardon me. It should be x minus 2, okay? All right, this is the first polynomial. You follow a similar pattern to find other polynomials, okay? If you want to find P2 here, you take the summation up to 2, okay? You expand and then find. You can get the help from this table to find those values. For example, if you want f2 of 2, f2 of 2 is going to be this one. When k is equal to 2, you have f2 of 2. You have 2 here. That is going to be this one. So likewise, you can find all the other Taylor polynomials. This is P2. I have calculated it for you. You can justify that it's going to be this expression. And if you calculate P3, it is going to be this expression. Okay, when you calculate P3, you take this summation up to 3. Okay, all right. Now, if you graph all these three polynomials and the actual graph of ln x is the function that we are looking at on the same plane. This is the picture that you get. As you can see, in green, the graph of the third order Taylor polynomial. As you can see, that graph is the closest graph to the original graph ln x. This is the graph of ln x in black, and this green graph is the closest graph. As you can see, when this degree of the Taylor polynomial is higher and higher, that better and better approximates the original function that you are analyzing. Okay, so that's the idea. So when you take your n to be bigger and bigger, you will see that your polynomial, Taylor polynomial, approximates the original function better and better. So that's the idea. Let's move on. Next, I want to go over this example, constructing a binomial series. Okay, for a non-zero constant p, the Maclaurin series for 1 plus x to the power p is called the binomial series. Okay, the Maclaurin series of this function is given a special name. That special name is binomial series. Okay. So this example is about calculating the binomial series for this function. My function in this case is this one. F of x is equal to 1 plus x to the power p. P is any non-zero constant. Okay. So we need to find the binomial series of this function, or in other words, we need to find the Maclaurin series of this function, and we need to show that it takes this form with this pk. Sometimes this is called p choose k in the combinatorics perspective, but we are not going to worry about combinatorics here. We just write pk, okay? Or sometimes you say p choose k, okay? So this, with this defined by, p choose k is defined by this formula. It is equal to this expression when if k is bigger than 0, if k is equal to 0, then it is going to be 1. Okay, so what does this mean? We need to find the Maclaurin series of this one, and we have to show that it takes this form with this quantity given by this formula. What is this quantity? What should this quantity be? If you take the definition of the Maclaurin series, remember the definition of the Maclaurin series is this one, right? Sigma k goes from 0 to infinity, fk of 0 divided by k factorial times x to the power k. As you can see, this resembles with this one, given that this quantity is exactly same as this quantity. Would you agree with me? Everything else is same. So here the point is, here the goal is, we need to show that this notation, p choose k, should be the same as fk of 0 divided by k factorial. This is our goal. If you can show that this is equal to this, and if you can get a general formula for fk 0 divided by k factorial, and if you can show that the general formula is exactly this formula, then we are done. Okay, so my goal is to get a general formula for this expression, k term, okay, fk0 divided by k factorial. How do we get a general formula? Again, we use a table. Okay, so we need to find this general term. So what we do is we find each derivative from the beginning. Okay, you start with k is equal to 0. You first list down your k values here. K is equal to 0, 1, 2, 3, 4 up to k. This is the general term, general index. And then you find fk of x, kth derivative of f. Okay, when k is equal to 0, f0x means the original function. Original function is just 1 plus x to the power p. Okay, now you can find fk of 0. You just plug in x is equal to 0 in this function. That is going to be 1. And then when k is equal to 1, that means you have 1 here. That is the derivative of f of x, right? So you take the derivative of this function. It is exactly this function. You know how to take derivatives now. So if you take the derivative of this function, it is p times 1 plus x to the power p minus 1. Now to find fk0, you plug in x is equal to 0 in this function. That will give you p if you plug in x is equal to 0. And then when k is equal to 2, f2x, that means the second derivative. This is the first derivative, right? To get the second derivative, you take the derivative of this one more time. That will give you the second derivative to be this one. Okay. Now to find fk of 0, you just plug in x is equal to 0 in this function. If you plug in x is equal to 0, this is what you get. And then similarly, when k is equal to 3, you will get the third derivative to be this one. You just take the derivative of the previous function. This function, that will be this. Now, to find fk of 0 for that row, you plug in x is equal to 0 in this function, which will give you this expression. Now you need to be able to identify a pattern. See, first term is 1, of course, and then p, next one p times p minus 1. Next one is p times p minus 1 times p minus 2. You should be able to tell me the next one, that is p times p minus 1, p minus 2 times p minus 3. If you continue this pattern, when we have general index k, it should be p times p minus 1 times p minus 2 times p minus k plus 1. right? But it is just by observing the pattern. So when you have the index k, it should be this product. Now we identify fk of 0. We have a general formula for that, but notice that that general formula is going to work only for these terms. For this one, for the first term, the general formula is not going to work. This general formula is not going to work for the first one, because if you plug in k is equal to 0, that will not give you 1. So we separate it out. Okay. How do we separate it out? Oh, first of all, let me calculate another column here. Okay. So the missing column here, that is this one. I'm calculating fk of 0, fk of 0 divided by k factorial. That's what I want, right? That is the coefficient of x to the power k. I need the general formula for this one. Now, to calculate that, I have to divide. I already have fk of 0. I have to just divide it by k factorial. So this is k is equal to 0. If you divide this by 0 factorial, it's just 1. And if you divide when k is equal to 1, if you divide this by 1 factorial, it is just p. And then this is when k is equal to 2. So you divide this by 2 factorial, you get this expression. So on and so forth. And this is the kth term. As you can see, this is the kth term. It is just p times p minus 1 times all the way up to p minus k plus 1 divided by k factorial. So now I have a general formula for this expression, but only for these terms, only when k is equal to 1, 2, 3, so on and so forth. But that formula is not valid when k is equal to 0. So I'm going to write the piecewise formula. Okay, this is going to be, this is the same thing as if k 0 divided by k factorial. I denote it by p choose k. As I mentioned to you earlier, I denote it by p choose k. P choose k. Okay, so that is going to be equal to this formula when k is equal to 1, 2, 3, 4, 5, so on and so forth. But when k is equal to 0, it should be 1. From this table, it is clear that when k is equal to 0, it should be 1. So I'm defining that as a piecewise formula. When k is equal to 0, this quantity should be 1. And when k is bigger than 0, that quantity should be that general term, because this general term can be used to generate all these terms. Okay? So this general formula is valid when k bigger than 0. When of course k is equal to 0, it should be 1 because of this. All right, so that completes that part. And this is a very important example, because we can use this idea to find the expansion for a function of this form for any given p. Okay, the next example is about that actually. Let's go ahead and look at that example. Okay, use the result from the previous example to find the binomial series f of x is equal to binomial series for f of x is equal to 1 plus x square root of 1 plus x. Okay, notice that square root of 1 plus x means 1 plus x to the power 1/2. That means your p-value is 1/2, right? If you compare the previous example, this p-value is 1/2 in this case. Okay, so all what you need to do is you need to plug in p is equal to 1/2 here. Okay, and if you plug in, by the way, first of all, notice that since I know that my fk of 0 over k factorial, which is what I denoted by p choose k, is given by this formula when k bigger than or bigger than 0, and it is 1 when k is equal to 0. Okay, so that means I can write the Taylor, the Maclaurin series for that. This is the Maclaurin series. Okay, when k is equal to 0, you just get f of 0. when k is equal to 1, then you plug in k is equal to 1, then you get the next term. And then this is when you plug in k is equal to 2, so on and so forth. All of these are known. F of 0 is just 1. So I'm writing my series here, okay? Expansion here. Let me highlight it. So this is going to be the first term, that is just f of 0. And then the next term is f prime of 0 divided by 1, okay? 1 factorial, which is, of course, f prime of 0 divided by 1 factorial is p. Because this is just f prime of 0, f1 of 0, f1 of 0 divided by 1 factorial, which is just p. So that's why you have p times x here. This is p times x, and then f2 0 divided by 2 factorial times x squared. f2 divided by 2 factorial is exactly this one. f2 divided by f2 of 0 divided by 2 factorial is this one. So you get the next term. P times p minus 1 divided by 2 factorial times x squared, so on and so forth. Okay, you can write down all the other terms. All right, now let's go back to our example. So we are asked to find basically you plug in p is equal to 1/2 in this formula that I just showed you. Okay, if you plug in p is equal to 1/2 in this formula, this is what you're going to get. Okay, and if you can further simplify this. If you simplify this further, this is as a polynomial. Of course, it continues. Okay, for higher order terms. All right, with that we conclude that section. Let's stop there, and I'll see you next time.